Okay, let's unpack this. Have you ever, found yourself right at the start of a coding project, staring at that blank screen and just feeling, well, kind of overwhelmed by all the choices you have to make right up front?
Oh,
Like
absolutely.
what tools? How are you going to handle errors? Is this thing even going to scale later?
Yeah,
And it feels a bit like one of those choose your own adventure books, but the consequences are pretty real for your code down the line.
that's a great analogy.
So today, you've actually brought us something really cool. It's an engineering blueprint for building a high-performance distributed C++ key value store. And it's not just some high-level plan, right? It's described as a 0 to 1 journey, really mapping out those critical foundational decisions.
Exactly. From the ground up.
Our mission here is to, cut through that complexity a bit, pull out the core insights, maybe some surprising bits from this blueprint, so that you, listening, can maybe apply some of this thinking to your own projects. Hopefully make those early choices feel a bit less daunting.
Yeah, and what's really striking about this blueprint is its commitment to a design-first philosophy. I mean, think about building, say, a skyscraper. You wouldn't just show up and start laying bricks randomly, would you?
Huh, hopefully not.
Right. You'd have incredibly detailed plans, structure, plumbing, electrical. Everything's mapped out before anyone even thinks about pouring concrete.
Okay, I see where you're going.
And it's really the same for software, or it should be. Those early choices, how you build it, the core data structures, your error strategy, these aren't small details. They fundamentally dictate, well, everything that follows.
Like scalability.
Maintainability.
Exactly. Scalability, maintainability, and honestly, how easy it is for someone else to jump in and contribute later. If you kind of skimp on that early blueprinting phase, you're basically building on shaky ground.
Hmm.
So the core problem this blueprint really tackles is how those initial decisions shape the engineering culture and technical substrate, as they put it, right from day one.
Yeah.
It's about setting yourself up for success long term. Okay, so if these choices are that critical, especially for something high performance and distributed in C++ Lake, how did this blueprint actually tackle some of them? Let's maybe start with something really basic, but often painful.
Yeah.
How do you just build the C++ project? Especially across different OCs, maybe for open source?
Yeah, that's a perfect place to start because a good build system, one that's easy for others to use, is foundational. Especially, like you said, for open source, where people are coming in with Windows, Mac, Linux, all different setups, different tool chains, compilers, linkers.
Right, and different shells. It'd get messy fast.
Totally. So the blueprint basically looked at two main contenders here.
Yeah.
The classic GNU Make and the more modern CMake.
Okay, Make, that's been around forever, right?
Yeah.
Direct control, but maybe a bit finicky.
Exactly. Make gives you very direct control. You write the rules explicitly. But, and this is the key thing the blueprint points out, it's inherently tied to a specific toolchain and shell environment.
Meaning it's a pain to make it work everywhere.
Pretty much. It often requires significant manual effort for cross-platform stuff. Works great on Linux with GCC usually. But getting that same Makefile running smoothly on Windows with, say, Visual Studio often needs workarounds, maybe MinGW or Cygwin to kind of simulate a Linux environment, adds friction.
Okay, so that leads us to CMake. The blueprint calls it a build system generator. What does that actually mean? How does that help?
Yeah, that's the magic trick. CMake isn't the build system itself. It generates the build files for the native system. You write one cmakelist.txt file that's like your master script.
Okay.
Then CMake reads that and spits out, say, make files for Linux or Visual Studio project files for Windows or Xcode projects for Mac OS. It abstracts away the platform specifics.
So it becomes platform agnostic.
Precisely, which is why the blueprint landed on CMake. For a project aiming for wide use, its unparalleled cross-platform support is huge. It dramatically reduces contributor friction.
Makes sense. It's almost like a statement about the project itself, isn't it?
It really is. It signals a commitment to modern C++ practices, accessibility, and collaboration. So that's a good tone.
Okay, tool chain sorted. Let's move inwards, to the actual heart of this key value store. Storing the data in memory, what was the thinking there? You got standard library options like std.map and std.unorderedmap. Big difference in performance, right?
Huge difference, yeah. And this is super fundamental. So std.map. Under the hood, it's usually a balanced binary search tree, often a red-black tree.
Meaning it keeps things sorted by key.
Exactly. It maintains sorted order, which means all your operations, finding, adding, removing, are typically Boolean. predictable performance. And it's great if you need to do things like range scans or ordered iteration, like give me all the keys between A and F.
Okay. And std.unordered map, different beast entirely.
Totally different. It's a hash table, no guarantees about order whatsoever. But its big advantage is superior performance for point lookups.
Point lookups being just getting one specific item by its key.
Exactly. Get me the value for this key. On average, std.unordered map gives you O1, or constant time, for inserts, lookups, and deletes, which is, significantly faster than OLRGN as your data grows.
But there's a catch, right? Worst case performance.
There is. If you get unlucky with hash collisions, lots of different keys hashing to the same bucket performance can degrade towards ON. But honestly, with decent hash functions, especially for standard types, that average O1 is what you usually see.
So for this blueprint, aiming for a high-performance key value store, where getting and setting individual keys fast is probably the main goal.
You nailed it. The choice was std.unordered map.
Because that raw speed for individual operations was the priority.
Precisely. The project mandate was high performance, and the most common operation is low latency access to individual items via their key. That overwhelming performance benefit in the average case of O1 just outweighed the need for sorted order that std.map provides. They consciously traded ordered iteration for speed on the primary operations.
Okay, clear trade-off there. Speed wins for the core task. Now, error handling. This get messy in C++, maybe, right? You've got error codes, exceptions. But this blueprint seems to push for something more modern.
Yeah, this is a really interesting one because how you handle errors really impacts robustness. So the blueprint looked at the options. Traditional error codes, yeah, they're fast, but notoriously prone to being ignored by the caller.
Again, they've done that.
Oh.
We've forgotten to check the return code. Oops.
Exactly. Then you have exceptions. Powerful, definitely. But the philosophy here, and I think it's a good one, is that they're really meant for truly exceptional, unexpected, and unrecoverable errors.
Not just like key not found.
Right.
Yeah.
Using exceptions for something predictable like key not found is arguably semantically inappropriate. Plus, it can actually hurt performance because of the overhead of stack unwinding.
Can you quickly explain stack unwinding again? What's the cost there?
Sure. So when an exception is thrown, the system has to stop normal execution and literally walk back up the chain of function calls that's the stack looking for a catch block that can handle it.
Okay.
And as it walks back, it has to correctly destroy all the local objects created in each function scope it leaves. That whole process, finding the handler and cleaning up, is complex and takes significant CPU time compared to, say, checking your return code. It's just not meant for routine expected failures.
Got it. So if error codes are easily ignored and exceptions are too heavy for common cases, what else is there? Did they consider std.optional? That came in C plus 17, right? For values that might be absent?
They did. std.optional is great for saying this function might return a value or it might return nothing. But its limitation, as the blueprint notes, is that it cannot convey why a value is absent.
Ah, right. It's just not there. No reason given.
Exactly. For a key value store, key not found is a specific expected kind of failure. You want to communicate that reason. And that's where std.expected from C++23 comes in.
Okay, so what does std.expected do differently?
It's essentially a type-safe union. It holds either the expected value, like the data you looked up, or an error value, like an error code or object explaining why it failed.
So it combines the is it there of optional with the why not of error codes, but in a type-safe way.
Precisely. And crucially, it forces the caller to actually check which state it's in value or error. You can't easily ignore it like an error code. You have to explicitly handle the error possibility.
Without the performance hit of exceptions for these non-exceptional failures.
Exactly. So the blueprint's decision, use std.expected for all those recoverable, predictable errors. Keep exceptions only for the truly catastrophic and unrecoverable runtime errors.
That sounds really clean, actually. Makes error handling explicit.
It really is. It's often called the state-of-the-art in C++ error handling now. It makes failure an explicit part of a function's type signature. Much more expressive, much safer.
Okay, wow. From build systems to error handling. Now let's zoom way out. The blueprint talks about taking this key value store to planet scale, distributed systems territory. And that immediately brings up the CAP theorem, right? This feels like a huge fork in the road.
It absolutely is. The CAP theorem is like fundamental physics for distributed systems. It basically says you have three desirable properties: consistency, C, availability A, and partition tolerance P.
Okay, what's a quick definition of each?
Right. So consistency C means all the different computers, nodes in your system have the same view of the data at the same time. If I write X5, the next read anywhere sees X5.
Got it, all in sync.
Availability A means every request you send to the system gets some kind of non-error response. The system is always up, always responding, even if parts of it are temporarily disconnected.
Always answers the phone.
Yeah. And partition tolerance, P, means the system keeps working even if the network connection between different parts of the system gets delayed or completely dropped, which, happens all the time in real networks.
Okay, C, A, and P. And the theorem says?
The theorem, proven by Eric Brewer and later formally by Gilbert and Lynch, says you can only reliably guarantee 2 out of these 3 properties simultaneously. And because network partitions, the P, are basically a fact of life, you have to tolerate in any non-trivial distributed system.
You're forced to choose between C and A, consistency or availability.
That's the essential trade-off, yes. You build systems that are either CP, consistent and partition tolerant, or AP, available and partition tolerant.
So what did the blueprint choose for this key value store, and why?
It chose to be a CP system, prioritizing consistency and partition tolerance over availability.
Interesting. Why consistency over availability for a key value store isn't being always available important?
It is important, but the reasoning here is that for many potential uses, especially if this store acts as a system of record, the definitive source of truth for some data, then the integrity of the data is paramount.
Meaning it's better to be temporarily unavailable than to return the wrong answer.
Exactly. The blueprint argues that returning stale or conflicting data can lead to severe, difficult-to-diagnose bugs higher up in the applications using the store. So they'd rather the system potentially block or return an error during a network partition, sacrificing A temporarily, than return inconsistent data, sacrificing C.
Okay, that aligns with how things like traditional databases usually work, right? They tend to favor consistency.
Very much so. It's a common choice when data correctness is absolutely critical. An AP system, by contrast, might always give you an answer, but during a partition, that answer might be old or conflict with what another part of the system thinks. Fine for some use cases, maybe not for others.
Right. Okay, so we've walked through these major decision points from the blueprint. CMake, unordered map, std.expected, and CP over AP. Now let's bring it back to you, the listener. Maybe you're that self-taught programmer figuring this stuff out. How do you decide which of these paths to take for your project?
Great question. Let's try and make it practical. Starting with CMake. Basically, if you think your project might grow, if you want other people to contribute easily, or if you even suspect you'll need it to run on Windows, Mac, and Linux, just use CMake.
Bite the bullet early.
Yeah, honestly, it saves so much headache down the road. It's pretty much the industry standard for modern cross-platform C++. Think of it as an investment in the project's future flexibility.
Okay, makes sense. What about std.unorderedMap versus std.map?
Simple rule of thumb. If your .1 priority is super fast lookups, inserts, and deletes based on a key, and you absolutely do not care about the order the keys are stored in, then std.unorderedMap is almost always your winner.
Like for a cache. Or looking up user data by ID.
Perfect examples. Anything where you just need to grab that specific thing really fast and order is irrelevant. If you need sorted order or guaranteed login performance, then you look at std.map.
Got it. Prioritize the common operation. Now, error handling with std.expected. When should someone reach for that?
This one's more about how you think about errors. If you have operations where something going wrong isn't a total disaster, but more like a predictable possible outcome.
Like the key not found example again.
Exactly. Or maybe invalid user input, or a file not being there yet. Things you expect might happen and need to handle gracefully. std.expected lets you make that possibility explicit in your function's return type.
So it forces you, the programmer using that function, to deal with it.
Right. It makes you consciously handle both the success case and the expected failure case. Leads to much more robust code without resorting to exceptions for things that aren't truly exceptional. Use it when failure is a valid, expected part of the story.
Okay. And finally, that big CAP theorem choice. CP versus AP, consistency or availability.
This really depends on what kind of data you're managing. If getting stale data or having conflicting views of the data would be catastrophic, think financial transactions, critical configuration settings, inventory management.
Things where being wrong is worse than being slow or temporarily down.
Precisely. If data correctness is absolutely non-negotiable, then designing for consistency, CP, is generally the safer bet. You accept that the system might pause or block during network issues to ensure it never gives out bad data. If availability is more critical and you can tolerate eventual consistency, then AT might be okay.
Wow, okay. That's a really helpful breakdown. What a deep dive, really. It's amazing how these choices, made so early, ripple through everything.
It really is. They seem technical, but they're almost philosophical declarations about what your project values. Tooling, data structures, errors, distributed behavior, they define that engineering culture we talked about. They shape how the project feels to work on and how it grows.
Setting yourself up for the long haul, not just getting something working now.
Exactly.
So ultimately, looking at a blueprint like this, it's not just about the specific answers they chose, is it? It's more about the process of thinking through these things deliberately before diving deep into the code.
Absolutely. It's the value of foresight, of anticipating challenges and building that solid foundation.
Which leads to a final thought for you listening. Reflecting on all this, what's one foundational decision in your own coding journey, maybe one you've struggled with, or perhaps even regret? And how might thinking through it more like a blueprint up front have changed things for you? Something to chew on.